Thank you. So we're going to be hearing from Raffa Ahmed, who's going to be speaking about using green LiDAR to map bathymetry of lakes.
Hello, everyone. My name is Raffa. I did my master program at NTNU at the hydropower development, and I was working as a research assistant during the last few months. And I want to... Okay. I want to talk a little bit about the assessment of green LiDAR application in lakes. And this work is done by me under supervision of Knut Alfredsen and Tor Hakon. Did they change? So what is the green LiDAR technology? The green LiDAR is remote sensing technology that uses the blue-green wavelength, which is able to penetrate the water and measure the seabed or the water body bed. So these scanners are mounted into the aircraft, and they start sending pulse or laser light to the water body, and these pulses are reflected from maybe the water surface or the water body itself or from the seabed. So it depends on the condition of the water. So these returns or these pulses are recorded and captured, and they go through analysis, and then they go through classification system. So overall, we will have multiple reflectance from the water body. So we can have a class, for example, for the water surface and then for the bathymetry. So these are general applications for the green LiDAR. For example, it can be used for the flood risk assessment. So if we have a good representation of the water body profile and the bathymetry, we can generate digital elevation model, and this can be used for the flood assessment and then calculating the damage cost. It can also be used for the erosion and sedimentation, the natural stream restoration, and we can say something about the formation of the bed and the grain size distribution and the habitat. And we can also track the movement of the bed if the rock is transporting from place to another, or yeah. Okay. The study areas have been selected according to the data availability in Norway. So in the upper part, we have Lake Selbusjøen and Lake Benna, and on the lower part we have Lake Krøderen, and each one of them is scanned by different sensors. So this is an overview of the sensors used for scanning these lakes and the corresponding dates of flights. And the comparison between the sensors were done in Cloud Compare, the software. So in the software, we extracted the elevation values into the point clouds, and these elevation values were interpolated between the two sensors. So they have been moved from one sensor to another. So we will have the data set in one layer of sensor, like in one point cloud, but from two different sensors. So then we did filtering for the classes, and this is so we can be left out only with the bathymetry data. So we filtered out the noise and the ground class. And it was a normal comparison. So the residual map was extracted by getting the subtraction value between sensor I and sensor J, for example. And we did the subsampling for the data to do the qualitative analysis. And this is one of the results. And we see that we have a Selbusjøen residual map, and this map includes the ground and the bathymetry. So if we eliminate the ground part, we'll be left out with the bathymetry. And we can see that the residual is normally distributed around 0, with a little bit skewness to the greenish area. That means seismel is measuring deeper than Chiroptera in some parts. And we see also like the blue line, I don't know if you can see it, but there is these blue areas near the shoreline has a larger discrepancy than the other part of the lake. And this, we'll come to that a little bit, but this was due to the water level change between the two flights. Here we have the correlation between the elevation between the two sensors, Sesmel and Chiroptera. And we see that the residual starts spreading out as we go shallower on the elevation values. So, for example, if we see between 156 up to 158, the elevation and the spreading of the residuals start to get wider. And here is the general overview of the result, summary of the mean value and the standard deviation and the median of each comparison in each lake. And it was to mention that the mean values between the sensors, the mean residual value did not exceed 15 centimeters. Yeah. Here we have the point densities as Selbischen, and these point densities were measured for 1 circular square meter. And we see that in Sesmel, it goes a little bit to the deeper elevation. That means it has an ability to penetrate more deeper than Chiroptera. And this discrepancy at the shallow areas was mentioned before, that it was due to the change in the water levels. And this is explained here, that Chiroptera was measuring in water level 158, while Sesmel was measuring average water level 156. So if we have in the shoreline for the same part, Chiroptera was measuring wet area, while Sesmel was measuring dry land. And this can lead to classification errors. And that explained the high residuals at the correlation part. For the hydrological conditions between the two flights, they were more or less the same, except for the water level. And the watercolor and the LiDAR performance are strongly connected. And to study that, we took some samples from the data set that we have already in Norway. And we got the watercolor as an example here. So we see that as the watercolor increase, the penetration depth start to decrease. So as the watercolor is getting darker, for example, the penetration depth start to decrease. And that is because we are talking about laser and light and the reflectance of the bottom and the photon energy going back again to the aircraft. To conclude, comparing different instruments, the green LiDAR instrument was giving mean value between 1 to 9 centimeters, while comparing the green LiDAR sensor with the multi-beam echo sounder, which is a different way of measurement, was giving a normal, sorry, I messed up. Comparing the different sensor or different way of measurement, the multi-beam echo sounder with the green LiDAR was giving 1 to 9 centimeter deviation, while comparing the green LiDAR itself together was giving a normal distribution of around 0. That means there is no systematic error. In the perfect conditions of lakes, and as an example in Lake Benna, it's a quite clear lake. The penetration depth was up to more than 20 meter depth. And yeah, to be able also to say something about the bed formation, we need a high number of points or high density, so we can detect how the bed is formed. But this was not really investigated deeply in this study, but it can be done for future studies. So as I mentioned, the water quality has a strong connection to the LiDAR performance in the bathymetry. So even though this data for the water quality were collected in different time than the flight time, but it was giving an indication that as we go higher, for example, in the watercolor, we get less penetration depth. But to be more precise in the future, we can have temporal and spatial match between the flight and the sample, so we can get more conclusion of that. The multi-beam echo sounder and the LiDAR, it can be worked together. They can be complementary to each other. So the multi-beam echo sounder can be used for measuring, for example, deep parts, and the LiDAR can be used for measuring moderately deep to shallow parts. So these can be used, for example, to do volume curves for the power plants, or maybe for flood analysis. Yeah, and yes, more details can be found in the NTNU report. Thank you.